Okay, welcome back to another special theory of relativity video. It is similar to the last video I posted about time dilation. This is chapter 39, problem 9. Previous problem was problem 7. I like doing the odd number problems because we have answers at the back of the book. This one says, how fast must a meter stick be moving if its length is measured to shrink to 0.5 meters? So that's it. That's the whole problem. It is one sentence, one question. So basically we have 1 meter stick. This is 1 meter. Boom, 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 boom. All the things, 1 meter. This is in a frame of reference, right? If I'm in the same frame of reference as the meter stick, I observe the meter stick to be 1 meter. But if there is someone in another frame of reference that is viewing this entire meter stick, the entire reference frame of the meter stick going here with some specific velocity. We don't know what the velocity is, but we're being asked the question, what is the velocity? This person will see the length of this meter stick contracted. What do they see? They see the meter stick to be exactly 0.5 meters. So it has reduced in size by half. That's what it looks like. This is relativistic effects. Last time we did a time dilation problem. This is a length contraction problem. So we're going to do the same thing, same kind of procedure. What am I curious about? Well, this is the problem setup. I drew a little picture. What are we looking for? We're looking for this right here. What is the information we have? 1 meter stick is moving with a velocity, and it appears to an observer at rest to have shrunk or length contracted due to relativistic effects to 0.5 meters. That is the information. What I would like to start with is the actual equation. So we have consequences of special theory of relativity. I'm going to scroll through until I find the length contraction section. And now I will pull up the length contraction equation, which looks like this, which I will actually also write in green. Length equals length subscript p. We now know this p means proper. Here we have a gamma. And this looks like LP multiplied by this factor that appears inside the gamma, v squared, c squared. Nice. That is the equation we can work with. As you can see, the equation includes parameters which are given to us in the problem. In the problem, we are given the length, the actual length, the proper length, boom, and we are given the the length contracted length, 0.5 meters. So now I don't think I'll have the same problems as I did in the time dilation equation because I kind of know what the properties of the system look like. And the last thing we have, which is the thing that we're looking for, is the velocity, which is included right here in the gamma term. So what we have is the length, which here I can actually say the length contracted length. This is the length that gets contracted, so it's 0.5 meters. On the other side, we have the proper length, which I will just do here. Proper length is 1 meter. And here we have 1 minus v squared c squared. Nice. Now what we can do is do a ratio again. I'm just going to divide this whole thing on this side. When I do that, what I get is 0.5 meters, 1 meter. I really like keeping units because here I can easily see that the units cancel out. Meters cancels with meters, and we get a ratio here, unitless quantity, which, as you'll see, it's kind of the case. Like here we have velocity squared divided by velocity squared. This is unitless. 1 is unitless. 1 minus something unitless is unitless. Square root of something unitless gives you something unitless. So you want to make sure all of the kind of units work out here. If over here you get something like meter squared, you know that somewhere like down the line you're moving some stuff around, you're doing some incorrect algebra. So we get 0.5 divided by 1, which is literally 0.5, unitless. This equals square root 1 minus v squared over c squared. Now I can take this entire equation right here. I have square both sides, so I have 0.5 squared. On this side, I have 1 minus v squared c squared. I can move some stuff around, so I'm going to add this term on this side, subtract this term on this side. So that gives me v squared c squared here, 1 minus 0.5 squared. I'm going to actually do this 0.5 squared. I don't know what it is. Maybe it's 0.25. That's my guess, but I don't want it to be wrong because of my calculation guesses. So 0.5, where's my square? To the power of 2 equals 0.25, makes sense. 1 minus 0.25 is 0.75. Here we have v squared. I multiply this c on this side, I get c squared. If I want to square root all of this, I get v is equal to square root 0.75, which from the last problem I remember is 0.866c. So I think this is the right answer. So how fast does a meter stick have to be moving such that an observer at rest to this frame of reference sees it length contracted by half its original length? The stick has to be going 86, 87% the speed of light, which is the same thing as what we saw in the clock problem. So you can see that time dilation and length contraction obey kind of the same principle. They reduce or dilate, whatever way you're looking at it, by half when you're moving at this speed. So as you change the speed, things change. Let's actually check if the answer is correct. I have my solution menu over here, problem number 9, which is 0.866 times c, 86% the speed of light. Looks great. Thank you guys for watching. Please let me know if you have any questions. If you have any other examples you could do. These are really awesome. Next video I might do related to relativity might be the simultaneity, the relativity of simultaneity. Crazy shit. So thank you as always for watching. Peace out.